So we have here a beautiful differential equations test. This is from spring 2025, and it's the third exam, meaning we're talking about what? Laplace transforms and also series solutions. And so it's going to be a fun test. Now, a lot of people get intimidated by this test, but I would say of all the tests, in some sense, this is the one that really tests on your question, do you know how to use your formula sheet? It will all come down to that. If you know how to use your formula sheet and your algebra, you'll succeed. And if you don't, you're going to struggle. So make sure you practice and get comfortable. And of course, as always, before you start the exam, make sure to put your name because, we want to get the credit for all the great work we're about to do. And let's begin. 6 problems. Going to be fun. Number 1. Find the inverse Laplace of 1 over s times s minus 1 squared. Now, there's a couple of ways to proceed, and that's sort of what makes it fun, right? You have options. And what are some options? Well, one option is you could say, oh, this is like a convolution. Yes. Do I recommend that? No, because oftentimes that leads to an integral, and you have some sort of an integration by parts. But really what you should see is like, ooh, this looks familiar. In particular, we have polynomial over polynomial, which means partial fractions. And so I'm going to go ahead and say it. That's one of the big ideas of Laplace transforms, right? We're taking this differential equation problem, we're turning it into an algebra problem. Now, what algebra problem do we get? It's usually a partial fractions related algebra problem. So you want to make sure you're comfortable with that. Partial fractions will show up inevitably on any one of these tests. All right, so we proceed. So we're going to do a lot of algebra and then a little bit of table lookup. So here's our basic setup. Let me say, well, we have an s term. So there's going to be something over s. Then we have an s minus 1 squared term. So that's going to make something over s minus 1 plus something over s minus 1 squared. Right? So if you see a power, you build up to that power. Now, some people might say, wait, shouldn't it be a cs plus d upstairs? No. Focus on what's on the inside. S minus 1. That is good to go. It's linear. You only start putting extra pieces upstairs when you have irreducible quadratics. Well, we clear off our denominators. And so for that, multiply everything by the original denominator, s times s minus 1 squared. And what do we get? We get that 1 is equal to a. Here the s's cancel. S minus 1 squared plus b. Here the s minus 1's cancel. And so we have s times s minus 1. And here the s minus 1 squareds cancel. So we get c times s. And, well, we have 3 unknowns, right? So what can we do? Well, there's a lot of approaches. And I'm not saying that 1 is best, but I am saying that 1 can help you get there a little bit faster, which is, if possible, make good choices, such as studying for your upcoming exam, an excellent choice. So what are some good choices we can make here? Well, choose values for s so that terms vanish. So for instance, notice how there's an s and an s. If we choose s equals 0, what happens? Well, over here we have 1 equals a times minus 1 squared, which is 1, and b times 0, and c times 0. And so we're like, oh, so we get that a equals 1. Well, isn't that convenient? Is there another good choice? Yes. Choose s equals plus 1. Then we get 1 is equal to a times 0 plus b times 1 times 0 plus c times 1. So 1 equals c. Ha-ha! Noise! And now you're like saying, ha-ha, Steve, you're out of good choices. But actually, we only have, what, one term left. And at that point, you can say, just throw in any value you want. So, well, we did 0, 1. Heck, I'll throw in 2. Excuse my language. Heck, oh my gosh. Sometimes when I'm doing a test, I get a little excited. 1 is equal to, well, here we'll have a times 1 squared. Okay, so that's a. But we'll just write it down as a, but we know what a is, so we'll come back to that in a second. Here we have plus b times 2 times 1. So 2b. And then we have 2c. All right. But we know a is 1. We know c is 1. So we say that's 1 plus 2. So that makes it 3 plus 2b. Subtract. We get that 2b. That term is minus 2, or b is negative 1. All right, good, good. So here's the punchline. What have we done? Well, we now know these numbers here. A is 1, b is minus 1, and c is plus 1. From here, what we can do now is we can say, let's go back to our original problem. Now that we've done the algebra, we say we really need to find the Laplace inverse of 1 over s plus 1 over s minus 1. And then, not plus, minus, be careful. I'll tell you, this is one of the challenges of exams, is reading your own handwriting and making sure you don't miss small things. All right, so 1 over s minus 1 over s minus 1 plus 1 over s minus 1 squared. Now we take advantage of linearity. So it's 1 over s minus 1 over s minus 1, and then plus 1 over s minus 1 squared. So the Laplace transform of those pieces. And some of these are probably familiar enough that we might know them, but just in case, we'll just start going through and saying, well, what do we have? And, let's find out how much of our sheet we're going to end up using, our formula sheet here. Well, we can say, the Laplace transform of 1 over s. Well, there's a 1 over s. So we say, okay, the Laplace inverse of 1 over s is going to be 1. Easy. Now, the next one, 1 over s minus 1. Well, that comes in there. We have, the Laplace transform of e to the something t is 1 over s minus that something. So this is going to become e to the t. Great. All right. And one thing you can think about is there's actually a fun rule which comes into play, which says, it's like we're shifting here. And if you do a shift, then that really means you add this exponential part, which, by the way, is what we're going to use in the next piece. We're going to say, we have a shift. That's going to come into play. So see how they have that s minus 1? That's like s minus b. So that says, what you really do is you take e to the t, right? Because s minus 1, e to the 1t. So that's e to the t. And then you say, imagine there wasn't a shift. So Laplace inverse of 1 over s squared. All right, that's how we can think of that. But what is the Laplace inverse of 1 over s squared? Well, good news. We look at that piece. Say, okay, what do we have here? Well, that's to get s squared, you put in a 1. And you say, okay, so that's 1 over s squared is the Laplace transform of t. And so this would become t e to the t. And so putting it all together, we have 1 minus e to the t plus t e to the t. And there we go. There we go. That's it, right? Not too bad. Just know your formula sheet, do partial fractions. You'll be great. All right. Number 2. Find the Laplace transform of the following function f of t, where f of t is piecewise. And if you ever see this curly brace here, breaking it up, it says, I'm doing it in terms of the pieces. Now, don't worry too much about the inequalities here. You're just looking for where do changes occur. And what we want to do is we first want to say we want to rewrite f in a very particular way. So instead of having f written in this way, our goal is to write it in sort of a one-line notation, and we're going to have on-off switches. So how do you do it? Well, you start by saying, what's our function? And you say, well, it's what's happening initially. So there's the initial part. It's 0. And then you say, okay, good. Where's my first change? And, well, you come up here and you look for where do things change. So your first change is at pi. You say, okay, good. So now I have my on-off switch at pi. So here, I like to call this my on-off switch. And so I can turn things on and I can turn things off. Now what am I turning on? I'm turning on the sine of t. Right, so this is the on. And then I'm subtracting the initial. This is the off. Now, of course, subtracting 0 doesn't really mean much right here, but I just want to go through and write down the process because I want to make sure. It's like, okay, yeah, there's a reason why things are the way they are. Okay, now where's our next change? Our next change will happen at 2 pi. Say, all right, well, for our next change, we do the following. Again, we have our on-off switch, u of t minus 2 pi. Okay, on-off. Now, what are we turning on? Well, we're turning on 0. What are we turning off? We're turning off what came just before it. So minus sine t. Now, we're close. We're almost like halfway there, but we're not quite there. What's the issue? Well, the issue here is this t, I don't want it as t. That's not what I need. I need it as t minus pi. And in a similar way, this t, I don't want it as t, I want it as t minus 2 pi. So that's our next piece. We're going to rewrite it in a more convenient way so that we have consistency. All right, so here we go. We don't need to put that in. And we'll say, all right, this is u of t minus pi. And now I'm going to say, well, what is sine? Well, I can write sine of t as t minus pi plus pi. Right? It's a true story. Right? T minus pi plus pi is the same as sine of t. And now here I have plus, and there's a minus, so I'll go ahead and pull the minus out. Minus u of t minus 2 pi. And this will be sine. I'm going to do something similar here, except 2 pi. T minus 2 pi plus 2 pi. Again, that's sine of t. And we're like, go. I really want just sine of t minus pi and sine of t minus 2 pi. I really want to do something with those pieces. Is there anything we can do with these two pieces to make them go away? And then we say, oh, wait, we didn't really read this part yet. You should read everything because there's lots of good information everywhere. It says, well, you know, if you add a pi, it's just changing the sign. And if you add a 2 pi, it really doesn't do anything. So we're like, nice. So what do we get? So this becomes a minus u of t minus pi sine of t minus pi. And here, it'll be a minus u of t minus 2 pi sine of t minus 2 pi. All right, now we're ready. Okay, so this is, in some sense, a lot of the work is rewriting it in just the right way. And so we've done this part. We haven't gone to the Laplace yet, but we wanted to write it in just the right way. Now you might say, well, wait, what is just the right way? That comes back to our formula sheet. And what are we looking for? We are looking for this piece right here. That is your piecewise formula. And it says, hey, if you have this on-off, u of t minus a, times that f of t minus a, that's why I want to write things as t minus pi's and t minus 2 pi's. Then you can say, there's going to be an exponential, and then you take the Laplace as if there were no shift. One of the things that you see is that you sort of have this duality, like an exponential on one side becomes a shift on the other side and vice versa. Okay, so now that we have it written in this way, here we go. So we have the following. The Laplace of f of t is the Laplace of all of this. So we'll just write it down again. No worries at all. Take our time. Enjoy the moment. And, what a lovely day. Okay, there we go. And we can again do piecewise. And so we can pull out the minus, the Laplace, u of t minus pi, sine of t minus pi, minus the Laplace, u of t minus 2 pi, sine of t minus 2 pi. All right, linearity, so you break things up into small pieces, and we come back and say, okay, we're going to have an e to the minus as, if you have a u of t minus a. So u of t minus pi, that tells us we're going to have a minus e to the minus pi s. And then what? Well, then it says, then do the Laplace of what it's attached to, but drop the shift. Minus, now here, we're going to have e to the minus 2 pi s, and then do the Laplace of what it's attached to, but drop the shift. And so sine of t. All right, now we're almost there. If we could say, do we know what the Laplace transform of sine of t is? And we do, because it's right there. The Laplace transform of sine of t, so that's b equals 1, is 1 over s squared plus 1 squared. Okay, so we end up with a minus e to the minus pi s times 1 over s squared plus 1 minus e to the minus 2 pi s 1 over s squared plus 1. And we're done. Now, we can put these together if we want, and I'll go ahead and do that. It's not technically required. If we boxed it here, we'd be great. I see in both cases we have a minus. I'm going to pull that out, and then we have an e to the minus pi s and an e to the minus 2 pi s. All right, those are those pieces. And then downstairs, in both cases, an s squared plus 1. Whoops, let me push that up. There we go. And there's a beautiful answer. Woohoo! Nice. Nice. All right. By the way, they love asking for a piecewise one. So it's like one of those things, you just know it's coming. You know it's coming. So be prepared. Be prepared. Don't be nervous. Don't be worried. Don't be scared. Be prepared. All right, number 3. And it's a two-parter. Okay, so part A. Find the inverse Laplace of s over s squared plus 4s plus 13. Now, does s squared plus 4s plus 13 factor nicely? It does not. So what do you do with it? Well, if it doesn't factor nicely, then you often say, well, let me try to complete the square downstairs. So let's think about that. So in other words, I have s squared plus 4s, and then I pause, and then I say, well, what would I want to add so that this would become a perfect square? So you take the 4, divide it by 2, and square it. 4 divided by 2 is 2. 2 squared is 4. Okay, and then you say, but wait, I don't have a plus 4, I have a plus 13. that leaves us with 9 left over. Or you say, oh, that's s plus 2 squared plus 9, which we can write as 3 squared. Okay, so that's actually pretty nice. Now, one thing you might be saying is, hey, partial fractions? And I'm looking at you like, partial fractions? And you're like, yeah. And I'm like, no, this is not. This is not a time for partial fractions. It actually already has been done. There's nothing further you can do. So you say, okay, so what do we have? Well, having completed the square downstairs, we have s over s plus 2 squared plus 3 squared. Now, here's the thing. This looks like things on the formula sheet. What does it look like? Well, it looks kind of like sine, and it also looks kind of like the cosine. Now, there's a bit of an issue here. You might say, hey, I see it. It's cosine, right? Right? Well, notice that here, this is s squared, and our current problem is s plus 2. And these, right now, are not matching, right? There's an s plus 2 down, there's an s up, not going to work. So we need to make them match. All right, so to be clear, we are looking at our s upstairs and our s plus 2 downstairs, and we say these are not simpatico. We need to align them. So we say, well, look, it's easier to do stuff upstairs, so that's where we're going to put our energy. And all right, so here's the idea. We're going to do a beautiful thing, which is called add 0. And the nice thing about adding 0 is we haven't changed anything. If you add 0, it's still the same problem. But if it's a well-chosen 0, you can move forward. So we want our s to look like s plus 2, so we say, okay, let's make it look like s plus 2. But now the problem is we have a different problem if we stopped here. So we say, well, okay, I'll subtract 2 right away. The plus 2 minus 2 cancel. Life is good. And we can take advantage of linearity upstairs. Because that minus in the numerator, that's a good minus. That's one that we can break our Laplace inverse over. So we're like, so this is really Laplace inverse of s plus 2 over s plus 2 squared plus 3 squared. And now we can pull out the minus 2, Laplace inverse of 1 over s plus 2 squared plus 3 squared. Okay, so we're getting closer. Now let's go back to our formula sheet. Let's see how we're doing. So we're going to be using here our sines and our cosines. And there's one other thing we're going to be using, which is, notice how here, let me rearrange, there we go. Notice how we have an s plus 2. That's a shift going on. So when you see a shift, that says you're going to get an exponential function showing up. And so far we're looking good. This looks like s over s squared plus b squared, except, we've done a shift. We'll fix the shift in a second. Here, we say, whoa, wait a second. I see it like it's roughly s squared plus b squared, but I don't have a 3 upstairs. I have a 1. We can fix that. So what do? We put a 3 upstairs. You're right. If we have a problem, we fix it. But then we say, make sure it's the same problem. So how can I compensate for that new 3? I can put a 1/3 times it. Because you can add 0 or times 1. And then I say, well, wait, I can pull the 1/3 out, so I can put a 1/3 out in front. So that 3 is to compensate there. And now we're in our home stretch. We're going to combine these 3 pieces. So what's going to go on? Well, since we have an s plus 2, well, that's really like s minus minus 2, right? We can make a little note here. S plus 2 is like s minus minus 2. And so, what does that tell us? Well, it tells us that we're going to get an e to the minus 2t. So we have, this is e to the minus 2t, and then it's like taking the inverse Laplace of the thing without the plus 2, s over s squared plus 3 squared. So that would be cosine 3t. Then the minus 2/3. Again, the s plus 2, e to the minus 2t, and it's the inverse Laplace of like b over s squared plus b squared, which is sine of 3t. And that's the answer. Okay, good, good. Not a lot you can do to simplify that, so a good place to stop. Which brings us now to part B. Okay, and oh my goodness, we have lots of stuff going on here. The e to the minus 4s, the square root of s minus pi. We're gonna take a moment here to sort of digest what's going on. And okay, so one thing, we'll just make a quick note. This is the inverse Laplace, the e to the minus 4s, and I'll think of this as s minus pi to the 1/2. Now, we have to understand what roles things play. So this s minus pi, what is this minus pi signaling? Well, the minus pi is signaling that this is a shift, and so we're going to have then, just notice how we had like this s plus s minus minus 2 let us do an e to the minus 2t. So s minus pi is going to do what? It's going to say, oh, we're going to get an e to the pi t showing up. But we have another thing happening at the same time, which is we have this exponential, right? So a shift leads to an exponential leads to a shift. And so the upstairs, that's also sending us a signal. What signal is going on upstairs? Well, that's trying to signal to us, oh, we're going to have the following. We're going to get u of t minus 4, f of t minus 4. So we have a couple of pieces intermeshing together here. So we're like, okay, we kind of have to digest things. And then, after we digest those two things, one more thing we have to keep track of. And I know, you're like, what? One more? What else? Well, let's talk about the Laplace inverse of 1 over s to the 1/2. And then we'll piece everything together. All right, so here we go. We'll have our formula sheet again. Laplace inverse of 1 over s to the 1/2 power. Where do we look? Well, where would that be? And it's not this s to the n plus 1. It's actually down here. We have this Laplace of t to an arbitrary number, beta, is gamma to the beta plus 1, s to the beta plus 1. And we're like thinking, okay, so what choice of beta makes this work? In other words, I need beta plus 1 to equal 1/2. Do we have something that does that? Well, yeah, we do. This would be, if we want beta plus 1 equal 1/2, that's the same thing as beta is minus 1/2. And we say, okay, cool. But we're missing something. What should be upstairs? We need a gamma to the 1/2. So we say, oh, so this is really the inverse Laplace of 1 over s to 1/2, so there's a s 1/2, but then there's a gamma to the 1/2 upstairs, and a 1 over gamma to the 1/2 out in front. I'm sorry, it's getting really crowded there. But we all know what we mean, right? We'll fix this up in a second here. do we know what gamma to 1/2 is? Yes, we do. It's right here on our formula sheet. Oh my gosh. Look how much we're using. We're using a lot. So gamma to 1/2 is root pi. So this becomes 1 over root pi. And then we have all this other stuff. But now we say, hey, according to this would be the inverse Laplace of that will be t to the beta, t to the minus 1/2. All right. So all our pieces are together. We're going to get an exponential coming into play. We're going to have a shift. And so we're ready to put it all together. So let's think about this. We have, I'll shift colors. Why not? It's a very colorful problem. We have our Laplace inverse of, and I'm going to think of this as e to the minus 4s times our 1 over s minus pi to the 1/2. Now, if we didn't have that e to the minus 4s, what would that be? Well, we would say, okay, you take the inverse Laplace of 1 over s to the 1/2, which would be 1 over square root of pi, t to the minus 1/2. But that e to the minus pi says multiply this by e to the pi t. Okay, so that's the inverse Laplace of just this piece. And then you say, okay, now that we have that, we need to incorporate this last part. So, all right, so that makes it u of t minus 4, because it's minus 4s, so t minus 4. And everywhere where you currently see a t, put a t minus 4. So 1 over square root of pi, t minus 4 to the minus 1/2, e to the pi, t minus 4. And there you go. So there's a lot of pieces in play on this one. This is a little bit of a subtle one, but you know, that's okay. We can handle that. We are good. We can handle it. Number 4. A tank is being used to make a delicious broth. Well, I am glad to hear that our broth is delicious, because I wouldn't be wanting to make an undelicious broth. That's just not cool. The tank initially has 15 gallons of pure water. All right, just water, plain water. And so this gives us some initial information. We'll see how that comes in a moment. 3 gallons per minute of pure water comes into the tank. 3 gallons of well-mixed broth comes out of the tank. Okay, so picture-wise, we can think of our tank. We can even sort of visualize it here. We have 15 gallons, and in we have 3 gallons per minute, and out is 3 gallons per minute. Okay, well that's good. Notice the water level never goes up, the water level never goes down, or I should say the broth level. It stays consistent. But what happens? Well, we haven't finished the story yet. What happens is at 3 minutes, boom, we add some seasoning, 5 ounces, and it'll be dropped into the tank. And then at 6 minutes, boom, 12 ounces of seasoning dropped into the tank. Now, notice we're just dropping into the tank. So it's like a one-time instantaneous thing. This is going to be important in what's going to come next. So you have to decide, hey, is this I'm turning something on and then turning something off, or is it a bam, bam? So that's going to come into play. Now, the question, if x of t is the amount of seasoning in ounces in the tank at time t in minutes, then set up and solve a differential equation for x of t. All right, we can do that. So let's think about what's going on. First off, it says set up, and then we're going to solve. So we have to do the setup first. You can't solve it until it's set up. But notice it says a differential equation. So that helps us know what we're doing. Differential equation means a derivative will be involved. So we say, well, okay, so we have x prime. Now x prime is the change. So when we're looking for change, we realize, oh, I can't spontaneously create seasoning. It's not like, oh, and then we said, and then there was seasoning, and so let it be done. No. It has to come from somewhere, or it has to go somewhere. So we have to look at, the in, and then we have to look at the out. Now, hopefully, I gave myself enough space, but we'll figure it out. So let's talk about the in. Well, there's a couple of places it could come from. Does anything come from the inflow? We have a rate of 3 gallons per minute, but what do we know about what's coming in? What's coming in is pure water. Pure water means no seasoning. It tastes like water. So we have 0 ounces per gallon times 3 gallons per minute. So this is coming from this piece right here. So that's the 0. All right, good. Then we say, oh, at time t equals 3 minutes, there's 5 ounces of seasoning. Now, remember we said it was a snap, right? We just drop it and it's done. So how do we capture that kind of an action? Well, that's the delta function. Like that's a burst, like a momentary action. And so we say, okay, so this is going to be a delta. And there's a 5, so the 5 delta. And then we say, what time does it happen? T minus 3. And similar, we're going to add 12. This is going in. And 12. And then, again, T minus 6. Delta T minus 6. Okay, so that's our inflow. What's our outflow? Okay, well, let's think. What's going out? Well, the only place things go out is over here. I say, oh, well, that's 3 gallons per minute. Now, think about what's the situation. It's well mixed. How much of the tank are we taking out? Well, there's 15 gallons in the tank, and we're pulling out 3 gallons every minute. So if we think about that, we're removing 3/15 of whatever's in the tank is exiting all the time. Well, that's 3/15 of the broth. And that means 3/15 of the liquid, which includes the water and the seasoning. So we're removing 3/15 of the seasoning. Is there any other place that the broth can go? That the seasoning can exit? No, that's the only thing where we have an out. This is an in, this is in, and this is our out. So there's only one out, but 3 potential places it could have gone in. And so now we've accounted for everything. And we can rewrite this. Of course, 3 over 15 is 1 over 5. And we'll move that across. So we get that x prime plus 1 over 5x, right? Moves across. Well, that's equal to 5 delta t minus 3 plus 12 delta t minus 6. Now, it did ask us to set up. So that is part of our answer. So the setup is done. Cool. We're making progress. Nice. What comes next? Well, what comes next will not surprise you. We're going to need to figure out a way to solve. And because we have delta, this is a case where Laplace transform comes in particularly well. And since we've just learned it, we should use our tool. All right, so here's our idea. We're going to take the Laplace transform of everything. So Laplace transform of x prime plus 1/5 Laplace transform of x is equal to 5 Laplace transform of delta t minus 3 plus 12 times the Laplace transform of delta t minus 6. Ta-da! Okay, now we turn to our formula sheet. Yes, it hasn't let us down so far, so let's see what we have on here that can help us. Well, here we're going to come to this part right here. The Laplace transform of the derivative is equal to what? Well, it's equal to s times f of s. So this first part right here, this is going to become s x of s. I'm thinking of the Laplace transform of little x is big X, minus x of 0. We'll come back to that in a second. Then plus 1/5 the Laplace transform of x, that's x of s, and all right, is equal to 5. Now, Laplace transform of delta t minus 3. Do we know the Laplace transform of delta? Yes, we do, and it's over here. Laplace transform of delta of t minus a is e to the minus as. So we say, so this is going to become e to the minus 3s. And plus 12, Laplace transform of delta t minus 6 is going to become e to the minus 6s. All right, we'll put this aside, and I think we're almost done with our formula sheet, by the way. Okay, let's see what we have. What can we say about x of 0? Well, we look for some initial information. So that's the initial. So, okay, so that's good. And when we start out initially, pure water. So that's the way of saying x of 0 is 0. So that goes away. Nice, nice. Now we look at this and say, we can factor out s plus 1/5 times x of s is equal to these other terms on the other side. And then we say, okay, divide by s plus 1/5. So that x of s is 5 e to the minus 3s over s plus 1/5 plus 12 e to the minus 6s s plus 1/5. And we're almost there. We've solved for capital X. But what is it we're after? We're trying to solve for little x. And we say, well, little x, that's the inverse Laplace of capital X. So what do? Well, x of t, inverse Laplace of our capital X of s. And, I've got to pause here. One of my favorite things I like to point out to people, and I have been guilty of this too. Notice we have a 5. And you're like, yes, Steve, you have a 5. I have seen many times when people have been working on exams in doing inverse Laplace type problems, they start to confuse their 5s and their s's. So, pro tip, learn to write well enough so you can distinguish the two. And that way you won't make a mistake. Excuse me. Sorry, I have something in my throat. So if you thought this was an S, you would be doing something very differently than if you thought this was a 5. So be careful. Be the right amount of careful. All right, now this becomes 5. We can pull that out because it's a constant. I'm going to think of this as the inverse Laplace of e to the minus 3s times 1 over s plus 1/5 plus 12 inverse Laplace of, again, e to the minus 6s times 1 over s plus 1/5. Now, here's the thing. Do we know what the inverse Laplace of just 1 over s plus the fifth is? Yes, we've mentioned it before, and that comes back to here. It looks like an exponential function. Now, what happens when you add this exponential function in the inverse Laplace? Okay, so that becomes a shift. So we're going to combine these two pieces here. And we say, okay, so what's going to go on? If you only saw this 1 over s plus a fifth, you would say, okay, this part right here, that looks like e to the minus 1/5 t. And similar, again, this part right here, that looks like e to the minus 1/5 t. But now we say, we combine, and we say, all right, here, this part says we're going to have an on-off switch at 3. So u of t minus 3, f of t minus 3. Here, we're going to have an on-off switch, u t minus 6, f t minus 6. So what do we get? And we get the following. We're going to get 5 on-off at 3, u of t minus 3. That's our, we're knocking in our 3, at time 3, we're putting in our 5 ounces, time 3, 5 ounces. And then this is going to become e to the minus 1/5, but instead of t, we do the shift. So t minus 3. Plus 12, and again we're shifting, u of t minus 6, e to the minus 1/5, t minus 6. And that's our solution. So that's our setup, our differential equation, and that's the solution to our differential equation. That's our solve. Whew! Yes, done, done. And we've made it through 4 of our Laplace transform questions, which means from here, we're going to be transitioning. There are 6 problems. There will be 4 Laplace transform in 2 series. It's predictable. And so, what's going to happen? Number 5. Given that y is the sum from 0 to infinity, ck x to the k is a solution to the differential equation y prime minus 2xy equals e to 3x, and y of 0 equals 0, find C0, C1, C2, and C3. Now, there's essentially 3 ways you can do this. One way, you can find a recurrence relation. Another way, you can just sort of turn the gears. But I'm going to go the third way, which is we're going to say, let's look at just enough. Okay, so first off, I have to say, what is just enough? And the answer is to say, well, we know what y of 0 is, and in particular, y of 0 is the same as C0. So that's actually a free point right there. You know, if you can say, oh, I can translate initial conditions to help get some into the initial C's, that's something. Now, what else? Well, here's what we're going to look at. We want C0, C1, C2, C3, and since this came from the initial conditions, what's going to happen is that as we look at this, C1 is going to come from looking at the constant term, which is really x to the 0. C2, you're going to look at x to the 1, and C3, you're going to look at x squared. So I'm just going to look at just enough to say what's going on with the initial pieces. And another way to think about what's going on is I'm saying, oh, everything's polynomial, and so I get different coefficients. You know, those C's are the coefficients of the polynomial, and I just need to look at the very beginning to get what I need. Okay, so with that in mind, let's start by noting the following. Well, what can we say? Y, well, I'll note that C0 plus C1x plus C2x squared plus C3x cubed plus dot, dot, dot. Okay, that's that part. What is y prime? C1 plus 2C2x plus 3C3x squared and dot, dot, dot. Okay. And also, we can say, well, what about e to the 3x? Well, good news. The formula sheet rides again. Because if you look at your formula sheet, you will note that we do have e to the z. And so you say, here it's like z is 3x. So we can use that and say, well, e to the 3x is the following. We can write that as the sum from 0 to infinity of 3x to the k over k factorial. Which is, again, we only really need to get up through the quadratic term. Plug in k equals 0, you get something to the 0 over 0 factorial is 1. 3x to the 1 over 1 factorial is 3x. And then 3x squared, that's 9x squared. And then divided by 2 factorial is divided by 2, and dot, dot, dot. Okay, so here we go. Here we go. We have our y prime, c1 plus 2c2x plus 3c3x squared plus dot, dot, dot. Okay, that's only need to go up through quadratic, minus 2x times y. Notice there's already an x here, so what do we need? Well, we need the c0 plus c1x, and we can actually just go dot, dot, dot from here on, because you're already up to, when you put that x in, you're already up to the quadratic. X times x squared would be cubic, is equal to 1 plus 3x plus, I'll put this as 9/2 x squared plus dot, dot, dot. Okay, so just to recap, what's every piece here? Well, we have our y prime. We have our minus 2xy equals e to the 3x. But everything now has been written in just the first initial batch. Well, now we expand and gather. So we say, okay, what's our constant term here? Well, constant term here is c1. There's no constant term there. How about our x terms? Well, we have a 2c2 here. And here we have a minus 2c0. And that's our x term. What's our x squared term? We have a 3c3 x squared. And here we have a minus 2c1 x squared. And then higher order stuff, the dot, dot, dot. And the higher order stuff, we don't need it. Equals, again, 1 plus 3x plus 9/2 x squared plus dot, dot, dot. And that leads us to the following. Well, we get that c1, the constant term, has to match the constant term. We already knew that c0 equals 0. I'm going to write that down for reference. We now know that c1 equals 1. Next, we go to the next term. 2c2 minus 2c0 has to match 3. Okay, so 2c2 minus c0 equals 3. But we know c0 is 0. Or 2c2 minus 0 equals 3. Or c2 is 3/2. Okay, good, good. Now we go to our next terms. 3c3 minus 2c1, that's got to be 9/2. So 3c3 minus 2c1 equals 9/2. Or we could say, hey, that becomes 3c3, which we don't know, minus 2, because c1 is 1, is equal to 9/2. Okay, now we can add 2 to both sides, or 3C3 is equal to 2, which is 4/2, plus 9/2, which makes that 13/2. Or divide both sides by 3, and we get that C3 is 13/6. So, our final answer, remember what we wanted to find, C0, C1, C2, C3. Our final answer is put this together. C0 equals 0, C1 equals 1, C2 equals 3/2, and C3 equals 13/6. Huzzah! Woohoo! Nice! Nice! We did it. Progress. All right, good. And that leaves us with our one last problem. Number 6. Assuming that this y equals the sum ck x to k is a solution to the differential equation 1 minus x squared y double prime minus x squared y equals 6, with y of 0 equals 0 and y prime of 0 equals minus 1, find C0, C1, C2, and C3. And a recurrence relationship. Okay, so once you know you have to do a recurrence relationship, it changes your strategy. We can't employ what we did on the previous problem. We got to keep working with the sums. All right, but let's at least go ahead and get a couple of free points out of the way. Initial conditions translate into the c's. So the y of 0 equals 0, well, that really tells us that c0 equals 0. Y prime of 0 equals minus 1. That tells us that C1 equals minus 1. And you might say, well, how do you get that? Well, if you plug in x equals 0, the only thing left is C0, so C0 has to be 0. If you took a derivative and then plugged in 0, you'd get C1, or technically you get 1 times C1, and so 1 times C1 has to equal minus 1. All right, so you get 2 freebies, right? And, that's actually worth something. It might not seem like much, but you're chipping away. Now, the fun part, right? Well, we have our y. What we need to do is get up to y double prime. So y is equal to our sum, 0 to infinity, ck x to the k. So that tells us that y prime, well, that's the sum k equals 0 to infinity of ck and k x to the k minus 1. And y double prime, that's going to be our sum k equals 0 to infinity of ck times k minus 1 x to the k minus 2. Right? Just term by term. Okay, so that's our idea. And we could shift our starting point if we wanted to, because you'll notice, for example, here, when you plug in either 0 or 1, it automatically goes away. Here, if you plug in 0, it automatically goes away. We'll hold off on that for a moment. For now, let's see what we're going to do. Okay, with this in mind, we're going to replace the y double prime with y double prime and the y with the y. It's a reasonable thing to do. So what do we get? Well, we get 1 minus x squared, y double prime, so that's the sum, k equals 0 to infinity, ck times k minus 1, x to the k minus 2, minus x squared times y, sum k equals 0 to infinity, ck x to the k, and all that equals 6. All right, now, here's our game plan. For the next couple of minutes, and we have a couple of minutes, we're not in any rush, we're going to have plenty of time to finish this. Our goal is to get one sum to rule them all, one sum to find them, one sum to bring them all, and in the light of differential equations, bind them. That's our goal, all right? That's our mindset. Our mindset is one sum. But not just one sum. We're going to be smart about this. And what we really want to have, right, our goal, we'll put it in here. What's our goal? Is we want to get, a few terms possibly at the start. It can happen. It may not. Plus a sum that starts from somewhere to infinity of stuff x to the k equals 6. Now, since we're already using k, actually let's change from k. We'll switch to, say, n, x to the n. So, not only do we want one sum, we want it consistent. So that's going to drive our choices in the course of the next couple of minutes. All right. And, well, what do we do? Well, here, let's take advantage of this idea of where we can distribute. So this is really the sum, k equals 0 to infinity, of ck, k minus 1, x to the k minus 2, minus x squared, sum k equals 0 to infinity, of ck times k minus 1, x to the k minus 2, and we still have the rest. So nothing we're going to do here is going to be particularly surprising, but there will be a lot of writing. So be patient with yourself. Next part, we're going to take any polynomial pieces and bring them in. That's one of the reasons why we wanted to distribute. By distributing, we were setting ourselves up so that we could easily bring in the powers of x's. All right, so now what do we have here? Well, the first term, nothing came in. So that still stays as it was. Sum k equals 0 to infinity, ck, k minus 1, x to the k minus 2. Here, we'll get the sum k equals 0 to infinity, ck, k minus 1, x to the k minus 2 plus 2, right, because this comes in. So that's x to the k. Minus the sum k equals 0 to infinity of ck x to the k plus 2. And all of that still equals 6. Okay, so let's continue where we were. Let's maybe do a quick recap. We'll continue doing recaps. We distributed so that we could bring in powers of x. So we brought in powers of x. Now comes one of the most important steps. We're going to re-index. And the reason we want to re-index is we want to make everything look the same. So we say, okay, here we see a k minus 2. So we're going to re-index so that n equals k minus 2. Here we see a k, so we're going to do a re-index. Well, not really much of one. It's k. And here we see a k plus 2, so we're going to re-index n equals k plus 2. All right, now, here we go. Fun stuff. We get our sum. Now, when k equals 0, what does n equal? Well, the answer is n equals minus 2. So minus 2 to infinity. Ck, well, here, if n equals k minus 2, we could say, well, that's the same as k equals n plus 2. So it's cn plus 2 times n plus 2, n plus 1, x to the n. Next one. Well, the only thing that happens here is everywhere where you see a k, you put an n. So this will be a more straightforward one. All right, what happens here? Well, we're going to start at k equals 0, which becomes n equals 2. to infinity. And now, what is k? Well, here k equals n minus 2. So it's c n minus 2 x to the n. All right, so after you brought in your powers of x, then you do your shifting. So don't shift until you've brought your powers of x in. Okay, so good news. Everything looks like x to the n. But we're not ready to bring it into one sum. The issue is the starts. They are starting at different places. So you say, well, where's the best place to start? You say, what's the highest start? Minus 2, 0, or 2? Well, the answer is 2. So you say, idea. What we're going to do is we're going to pull off terms. So we're ready to keep pulling terms off until we get to our start of 2. So imagine we plugged in n equals minus 2, we'd get 0. Right, because minus 2 plus 2 is 0. Plug in minus 1, you'd get 0. Okay, this is doing great. We're doing wonderful. What if you plugged in 0? Well, you'd actually get something. What would you get? Well, you'd get C2 times 2 times 1 times x to the 0. So this is the n equals 0 term. Plus, plug in n equals 1. You get C3 times 3 times 2 times x. This is the n equals 1 term. Plus, then, n equals 2 to infinity of Cn plus 2 times n plus 2 times n plus 1 x to the n. That's just the first part. Now, here, plug in 0, you get 0. Plug in 1, you get 1. So, if you plug in 1, you get 0. Plug in 0, you get 0. Plug in 1, you get 0. So we can just, the first terms, 0 and 1, were 0 anyways. So we can just rewrite from sum 2 to infinity, Cn n minus 1 x to the n. And here we don't have to do any reindexing. It's already at the right start. Sorry, not reindexing. We don't have to do any pulling off. It's already at the right start. And we still have our 6 on the other side. And so we're ready, right? Here we go. We have 2c2 plus 6c3x plus the sum n equals 2 to infinity. All the starts match, so we can do this. Everything has an x to the n, so we can do this. We get Cn plus 2 times n plus 2, n plus 1, minus Cn times n minus 1, minus Cn minus 2, x to the n equals 6. All right, we're ready to put everything together. And you're like, Steve, we got it. We're almost out of paper. That's okay. We're also almost out of problem to do. Let's recall what we said. From the initial conditions, you get C0, C1. So, we already have the following. C0 equals 0. C1 equals negative 1. Those were given to us. Now, we're going to play a matching game. Notice here, on the left-hand side, our constant is 2c2. That has to match our constant on the right-hand side, which is 6. Okay, so 2c2 has to equal 6. What does that tell us about c2? c2 better be 3. Okay, so c2 is 3. Now, you say, okay, let's match again. I like this matching game. Matching game. 6c3x. That's the x term on the left-hand side. What's the x term on the right-hand side? 0. So 6c3 has to equal 0. What does that tell us about c3? c3 is 0. All right. Now, I say, oh, okay, so where's the recurrence relationship? And that is in here. These are your coefficients for anything from x squared and above. What do the things from x squared and above look like? Well, there's nothing x squared and above on the right-hand side, so all of these are 0. And so, if you write down what that means, that says we get Cn plus 2 times n plus 2, n plus 1, minus Cn times n minus 1, minus Cn minus 2 has to equal 0. And this is for n at least 2. So these are your initial values that they wanted us to find, and this is our recurrence. And that's it. That was what they asked us to find. So we did it, and it all fit on the one page. So this one, it feels like a lot, but if you start thinking about the individual steps, like each one is not bad, right? So what did we do? We took our derivatives, we plugged in, replaced our y and our y double primes by our sums. We distributed, moved the powers of x in, re-indexed, then pulled off terms at the start so that all the starts agreed. And then once all the starts agreed, we said, well, we have stuff at the beginning plus everything from where our starts agree on. That's our recurrence relationship. And then this will give us a few terms at the start to help us get our wheels turning for our recurrence. And that's the process. And it works. And you can do it. You can do it. Come on, this is it. The end is here. Finish strong and do wonderful. And I hope you do wonderful. I hope, that for some of you, this will be your last exam, your last math exam. Have fun, and I hope you do well. And if I never get another chance to say it, I'm glad I got to spend time with you. Thank you for being with me. Good luck. It's been a wonderful time, and it's been my pleasure to help you out. All right. Bye.